Swayam Prabha. Digital India. Educated India.
In this lecture, I will now discuss the various types of spatial filters which can be applied to a digital data. Edges are places in the image with strong intensity contrasts. Since edges often occur at image locations representing image boundaries, edge detection is extensively used in image segmentation when we want to divide the image into areas corresponding to different objects. Representing an image by its edges has the further advantage that the amount of data is reduced significantly while retaining most of the image information. Since edges consist of mainly high frequencies, hence edges can be detected in theory by applying a high pass frequency filter in the Fourier domain or by convolving the image with an appropriate kernel in the spatial domain. In practice, edge detection is performed in the spatial domain as it is computationally less expensive and often yields better results. Since edges correspond to strong illumination gradients, these can be highlighted by calculating the derivative of the image. It can be seen that the position of the edge can be estimated with the maximum of the first derivative or the zero crossing of the second derivative. In this particular slide, just to provide a simple understanding as to what we mean by edge detection, a image has been allowed to be convolved with a 3 by 3 edge detecting filter, and what we can see is that all the features which wherever there is a change in the boundary of the features, a line exists, and thereby what we can find is rivers and forest boundaries, all these are getting highlighted very uniquely. Well, this can be further improved upon by increasing the kernel size of the edge detecting filter, and what we can find is now the edges are becoming more stronger than the previous case. Well, in this particular slide we can see that the edge detection filter of size 7 by 7 is now increase the thickness of the edge for many of the linear objects which is there, and it appears as if the objects are now being filled up. That is, the crispness of the edges are now slowly being reduced. So, with this background, let us proceed ahead to see that the task that we have is to find a technique to calculate the derivative of a two-dimensional image. Therefore, the task is to find a technique to calculate the derivative of a two-dimensional image. For a discrete one-dimensional function f I, the first derivative can be approximated by the relationship taking the differential equation of the function I over the I, which is equal to function I plus 1 minus I. Calculating this formula is equivalent to convolving the function with a kernel of minus 1 1. Similarly, the second derivative can be estimated by convolving the function f I with a kernel of 1, minus 2, 1. In spatial domain, differentiation process sharpens the given image, thus enhances the edges or linear features. It is known that averaging is analogous to integration and that it tends to blur details of an image, and therefore, it is natural to expect that differentiation will have the opposite effect and will sharpen a given image. The most commonly used term in the method of differentiation is gradient. Given a function f x, the gradient of f at the coordinate x y is defined by the vector, that is gradient of the function f x is equal to delta f over delta x, delta f over delta y. The important properties of gradient are: first, the vector g points towards the direction of maximum rate of increase in the function f x, and that the magnitude of the gradient of the function f x equals to the maximum rate of increase of the function x y per unit distance in the direction of g, and can be denoted by the gradient f x, a gradient of the function x y, where this is equal to the magnitude of g and can be represented as the differential of the function f with x whole square plus the differential of f with y whole square taking the square root. These properties have been used for the design of various filters, non-directional and directional. Also, some zero crossing filters are described, which use the method of zero crossing in place of gradient. The edge detection techniques can be categorized into two classes: frequency domain and spatial domain. In remote sensing, use of spatial domain technique is easier and economical. Therefore, only spatial domain techniques have been discussed here. These techniques can further be classified as non-directional and directional filtering and zero crossing filtering. So, now let us look at the classification of various edge detection techniques which are there. The techniques for detection of edges or linear features can be classified as: first, non-directional filters. It can be performed by using either a Laplacian filter or a high boost filter. Second, directional filter. It can be performed by using a simple directional filter or gradient filters, which may consist of the following operators such as Roberts, Sobel, Pritt and Kirsch. Third is zero crossing filter. It can be performed either by using a log filter or DDOG filter. Non-directional filtering operations consist of implementation of Laplacian filter and high boost filter. These filters are known as non-directional as they do not enhance any specific feature having a particular orientation. Directional filters is performed by a simple directional filter and gradient filters. These filters work on the basis of a linear gradient, that is, at each point the gradient is obtained to locate the intensity and the direction of the edge. This technique, however, is sensitive to noise, because the process of differentiation amplifies the noise in an image, resulting in the detection of false edges. The process of removal of noise should be applied with the help of a suitable noise removal filter. Directional filter is used to enhance the linear features having a definite orientation in the image. Zero crossing filters may be direction or non-directional using a second order derivative of a Gaussian function. So, let us look at non-directional filters first. Under this category, the main filter is the Laplacian filter. Laplacian filters are the non-directional filters as they enhance the linear feature having any orientation in the image. The exception applies to linear features obtained parallel to the direction of filter movement, as these features are not enhanced. Laplacian of any function f is given by the derivative of the function f, where the second derivative of the function is equal to the second differential of the function with respect to x, and the second differential second order derivative of the function with respect to y. Analogously, for a digital picture where the second derivative of the function with respect to x and y, these are the second order derivatives of x of f in the x and y direction respectively. So, this can be now written as the second derivative of the function at location x y, which is equal to the second partial derivatives of the function with respect to x plus the second partial derivative of the function f with respect to y respectively. These second partial derivatives can be written in the form of difference equation, that is, the differential first partial differentiation of function f is nothing but the function at x y minus the function at x minus y, x minus 1 minus y, or alternately it can be written as function at the location x plus y, x plus 1 comma y minus the function x y minus the function f at x y minus the function at x minus 1 y. Thus, on simplifying this, what we find is that this can be further simplified, and we can say that the second order derivative of the function at x y can be written as function at location x plus y, x plus 1 plus y minus 2 twice the function at x y plus the function at x minus 1 comma y. Similarly, the function the second partial derivative can be for the function can be written in terms of y also, and it can be expressed in this manner as it has been done in terms of x. So, the second derivative of the function with respect to y can be now expressed as function at x comma y plus 1 minus twice the function at x comma y plus the function at x comma y minus 1. On combining these two equations, we get that the second derivative of the function at x y can be now written as function x plus 1 comma y plus function at x minus 1 comma y plus function at x comma y plus 1 plus the function at x comma y minus 1 minus 4 times the function at x y, or this can be simplified into a kernel or a mask which can be utilized, and this is represented in the second graphics that we have, wherein the various function the values of the filter have been indicated. Now, this filter, when it is applied over the input image, it creates a new image, which is the output image as represented here. This is conceptually very much similar to convolution filtering operation, only the operating window is different. The sum of all the elements within the filter window here is 0. Hence, it is a kind of high pass filtering. Basically, the Laplacian filtering operation computes the differences between the digital counts of the central pixel and the average of the dn values of the 4 adjacent pixels in the horizontal and vertical direction. So, the above equation can be explained as y is equal to x minus a 4 plus x minus a 5 plus x minus a 2 plus x minus a 7. So, the output image is nothing but the sum of the partial derivatives in the horizontal and vertical pixels within the operator. Figure A shows a simple Laplacian mask which can be there. However, in order to accommodate for edges at any other direction than the vertical or horizontal direction, what we can do is we can rotate the original mask by 45 degrees and create another Laplacian mask with orientation invariant. So, the output image is nothing but the sum of the partial differences in the horizontal and vertical pixels within the operator, and this is illustrated in figure A. If the analyst is interested in also including the edges which are at 45 degrees and 135 degrees, this particular mask may be rotated by 45 degrees about the central pixel, and this creates a new filter which is known as the Laplacian mask with orientation invariant. Here what we find is all the 8 neighborhood pixels are now having value of 1, while the central pixel is having a value of minus 8. This window calculates the derivative in 4 orientations, that is along horizontal and vertical lines. In order to make this operator rotation invariant, the window is rotated about 45 degrees in any direction, clockwise or anti-clockwise, and combined with the original window, thus giving a window as shown in figure B. This window takes derivatives in 8 orientations, that is horizontal, vertical and 2 diagonal directions. This filter, being a second difference operator, has 0 response to linear ramps, but it responds to the shoulders at the top and at the bottom of a ramp, where there is a change in the rate of change of gray level. The digital Laplacian does respond to edges, but it responds more strongly to corners, lines, line ends and isolated points. It also responds to noise as effectively as it does to edges. The next slide that we are seeing here, a Laplacian filter 3 by 3 has been applied, and we can see how clearly the edges of various features, specifically the river streams, are very clearly depicted. Similarly, the canal which is flowing at the bottom part of the image can also be seen very clearly now. The next type of non-directional filter is the high boost filter. A high boost filter may be created by using a weight k on the original image in a high pass filter computation. That is, high boost is equal to k times the original minus a low pass, which can be said to be k minus 1 original plus original minus the low pass, which can be then simplified to be said that this is k minus 1 the original image plus high pass. This results in partial restoration of the low frequency components, which may have been lost in a high pass orientation. A standard high pass image results if k equals 1. For values of k greater than 1, the processed image looks like the original image with a degree of edge enhancement that is dependent on the value of k. The same algorithm can be described by the following equation, that is r star is equal to r minus f multiplied by r dash plus c, where r star is the filtered pixel value at the center of the window, r is the original value, f is a proportion varying between 0 and 1, and c is a constant whose function is to ensure that the value of r star is always positive. Next, we come to the simple directional filtering. Direction filters are used to enhance specific linear trends within an image. A typical filter consists of two kernels, each of which is an array of 3 by 3 pixels. The left kernel is multiplied by cos A, where A is the angle relative to the north of the linear feature to be enhanced. The right kernel is multiplied by sin A. The angles in the northeast quadrants are considered negative, while angles in the northwest quadrants are considered to be positive. This slide, as a matter of fact, shows a schematic representation of a simple directional filter. In this method, first the left filter kernel is placed over the original image, and each pixel is multiplied by the corresponding filter value, and these 9 values are summed up. This summation is first combined with the original central pixel value of the image window, and the resulting value is now multiplied by cos A. Well, now this value is replaces the original central value of the image. The kernel moves on the entire image, and image is filtered by the left kernel is obtained. Now, the process is repeated with the right kernel, except that the multiplication is done by sin A instead of cos A, and the image filtered by the right kernel is obtained. Then the two filtered images are summed to get the directionally filtered image. Gradient filtering. This type of filtering is based on the gradient. These filters yield a high value at places where the gray level values are changing rapidly. Before going into the details of these techniques, it is appropriate to understand the significance of gradient. If delta f by delta x and delta f by delta y are the rate of change of a function f in any two perpendicular directions, then the rate of change can be defined by the tan inverse of the differential of the function f with respect to y divided by the differential of f with respect to x, and its magnitude can be expressed by taking the square of the differential with respect to the x and square of that plus the square of the differential of y of f with respect to y and taking the square root of the two. If the directional derivative is used as a measure of edge strength, its response would vary with the orientation of the edge. To avoid this, the magnitude of the gradient may simply be used, as this automatically changes the rate of change in the direction of the greatest slope, Analogously, for a digital picture, first differences can be used instead of first derivatives as given below. That is, the first difference of the function with respect to x can be expressed as the function at x y minus function at x minus 1 comma y, and the first difference of the function with respect to y can be expressed as function x y minus function x comma y minus 1, where the first derivative of the function with respect to x and with respect to y represent the gradient in x and y direction respectively. These are digital convolution operators which convolve the function f with the patterns minus 1, 1 and 1 minus 1 respectively. Any partial derivative operator d can now be expressed by the function, that is, it is the differential of the nth order divided by the difference of the with respect to x and difference with respect to y, and it is a linear operator, and it follows that any linear combination of d is also a linear operator. Any arbitrary combination of d is a local operator, since its value for a picture f at point x y depends only on the values of f in any small neighborhood of x and y. It is of particular interest to construct these operators that are isotropic, that is rotation invariant, in the sense that rotating the function f and then multiplying the operator gives the same result as applying the operator of f and rotating the output. These operators must be isotropic, so that they can sharpen the blurred features such as edges and lines which may run in any direction. The isotropic operators have the following properties. An isotropic linear derivative operator can involve only derivatives of even orders. In an arbitrary isotropic derivative operator, derivatives of odd orders can occur only raised to the even powers. Following are the most common types of operators used for gradient filtering: Roberts operator, Pritt operator, Sobel operator and Kirsch operator. So, let us look at Roberts operator. As given earlier, in the first difference is used instead of the first derivative for the digital picture. So, by taking the first difference of the function with respect to x and y and combining together by taking the square root of the sum of the squares. However, it does not seem to correct to combine the first derivative of the function with respect to x and y at the position x y, since the difference measured by that operator is not symmetrically located with respect to x and y. The derivative of x uses a pair of pixels which is centered at x minus y minus half, while the derivative of y uses a pair centered at x minus half comma y. This can be avoided by using difference operator rather than derivatives of the x and y. One possibility is to use a forward derivative and a backward derivative, whereby the forward derivative of the function x y can be represented as the function at the location x plus 1 comma y plus 1 minus the function value at x comma y. Similarly, the derivative in the backward direction of the function f x is equal to the function at x comma y plus 1 minus function at x plus 1 comma y. These windows measure the 45 degrees and 135 degrees diagonal changes in the function using pair of points that are symmetrically surround at x plus half comma y plus half, yielding a filter using a filter nomenclature of 0 1 minus 1 0 and 1 0 0 minus 1. Well, this nomenclature of the filter is what we call it as the Roberts operator. In this slide, the horizontal edges using a 3 by 3 window has been depicted, and what we can see is that all the horizontal edges in the image are highlighted with the white color. When we increase the filter size to 5 by 5, these become more enhanced, but however, the image quality reduces very drastically and it becomes still more blurred once the filter size is made 7 by 7. Similarly, we can use the vertical edge filter of a 3 by 3, and all the vertical edges in this case are depicted by the white color. And the next slide shows the vertical edge for a filter size of 5 by 5, and the next one shows the vertical edge for 7 by 7. And what we can find is now that these edges are becoming much hazy in comparison to what we have seen for a filter of window size of 3 by 3. Now, we can rotate this Roberts filter by 45 degrees to obtain the left diagonal edges, that is diagonal oriented towards the left, that is 45 degrees from the vertical towards the left side, and all the diagonal edges can now be seen in this particular case. What we can find is that very few such left diagonal edges are present. When we look at the right diagonal edges, then we find that specifically in the mountainous regions where the edges are not parallel to the horizontal or to the vertical edge of the image, but it is at these have been highlighted very prominently and can be seen very clearly and can be used to extract the desired information. The next operator is the pivot operator. The effect of noise on the response can be reduced by smoothing the picture before applying the operator. In particular, local average can be taken before differencing or equivalently. An operator can be used computes the differences of the local averages. Suppose the average over a 2 by 2 neighborhood pixel is taken, then the function at the 4, this would be represented by the equation half function f x plus function x plus 1 comma y plus function f x comma y plus 1 plus function at x plus 1 comma y plus 1. For these type of operations, the average should not be used at the adjacent pixels, since the neighborhoods on such pixels overlap and the differencing will cancel out the common values and weaken the response. For example, we have that the functionality of the 4 directions at x comma y and x minus 1 comma y, this yields a relationship 1 divided by 4, the function at x plus 1 comma y plus function at x plus 1 comma y plus 1 minus function at x minus 1 comma y minus function at x minus 1 comma y plus 1, which is a weakened difference of 2 pixel averages that comes from the adjacent, but non-overlapping neighborhoods. With this, what we can do is, we can now create the structure of the pivot operator, wherein it will have the values of minus 1 along the left direction, left column, and plus values in the right column. Similarly, for horizontal edges, it will have minus values in the top row and plus values in the bottom row. This type of operator which is based on the difference of averages, will respond blurrily to an edge at several positions. The blurredness of the responses can be reduced to edges while still retaining some of the smoothing power by averaging only in the direction along the edge. It can be represented by the windows. They respond strongly to vertical and horizontal edges separately and weakly to directional edges. The image can be convolved by both the windows separately, and the sum of the absolute values or the root mean square of the two windows can be used to determine the magnitude of the edges. So, this particular slide shows the pivot operator once it has been applied, and what we can see is that now in this case all the horizontal and vertical direction edges along with the edges in any direction, they are getting highlighted very suitably. The next operator is the Sobel operator. The Sobel operator is used in image processing, is technically is a discrete differentiation operator computing an approximation of the gradient of the image intensity function. At each point in the image, the result of the Sobel operator is either the corresponding gradient vector or the norm of this vector. The Sobel operator is based on convolving the image with small separable and integer valued filter in horizontal and vertical direction, and is therefore relatively inexpensive in terms of computations. On the other hand, the gradient approximation which it produces is relatively crude, in particularly for high frequency variations in the image. In simple terms, the operator calculates the gradient of the image intensity at each point, giving the direction of the largest possible increase from light to dark and the rate of change in that direction. The result therefore shows how abruptly or smoothly the image changes at that point, and therefore, how likely it is a part of the image represents an edge, and as well as how that edge is likely to be oriented. Mathematically, the gradient of a two variable function, here it is the image intensity function, is at each image point a 2D vector with the components given by the derivatives in the horizontal and vertical direction. At each image point, the gradient vector points in the direction of the largest possible intensity increase, and the length of the gradient vector corresponds to the rate of change in that direction. This implies that the result of the Sobel operator at an image point which is in the region of constant image intensity is a 0 vector, and at a point on an edge is an vector which points across the edge from darker to brighter values. Mathematically, the operator uses two 3 by 3 kernel which are convolved with the original image to calculate the approximations of the derivatives, one for the horizontal changes and other for the vertical. If we define A as the source image and G x and G y are the two images which at each point contain the horizontal and the vertical derivative approximations, the computations are as follows. G x is equal to a matrix of 3 by 3 having elements plus 1, 0, minus 1, plus 2, 0, minus 2, plus 1, 0, minus 2 multiplied by the original source image A, and G y is a matrix of 3 by 3 multiplication, wherein the elements are plus 1, plus 2, plus 1, 0, 0, 0, minus 1, minus 2, minus 1 multiplied by the original source image. Here star denotes the two dimensional convolution operation. The x coordinate here is defined as increasing in the right direction, and the y coordinate is defined as increasing in the downward direction. At each point in the image, the resultant gradient approximations can be combined to give the gradient magnitude using g is equal to square root of g x square plus g y square. Using this information, we can also calculate the gradient direction, that is theta is equal to arctan of g x divided by g y, where for example, theta is 0 for a vertical edge which is darker on the left side. The Sobel operator represents a rather inaccurate approximation of the image gradient, but is still of sufficient quality to be of practical use in many applications. The more precisely, it uses intensity values only in a 3 by 3 region around each image point to approximate the corresponding image gradient, and it uses only integer values for the coefficients which weight the image intensities to produce the gradient approximation. Here we can see the structure of the Sobel operator, and applying this Sobel operator, now we can get the corresponding edges in the image. Well, these edges are approximate edges, as we have said, but still the amount of information which can be seen specifically in the mountainous regions, the edges of the ridge lines and the valleys are of importance to people who would like to map this particular area. The next operator is Kirchhoff operator. All the operators which have been discussed so far are having one or two windows which are more sensitive to edges in the two principal direction. Kirchhoff operator consists of 8 windows. The operator is equally sensitive to edges in all the 4 directions, that is 8 orientations. It gives negative weights to each 5 consecutive neighbors and positive weights to the other 3, with the weights chosen so that they all sum up to 0. The central pixel can thus be given a 0 weight. All the windows are applied separately at each point, and the root mean square value is adopted, which is the measure of an edge. These windows are shown in the figure which is there, and we can see that 3 elements are having -5, while the 5 elements are having a value of positive 3, giving the central pixel a value of 0, and these elements now keep rotating in the clockwise direction to generate the 8 mask of Kirchhoff operator. Then we come to the next type of filters, and that is zero crossing filters. Most of the edge detectors use gradient as the means of detecting edges. If we take the second derivative of the intensity function, we obtain a negative or positive sloped zero crossing at the gradient extreme, that is the edges, which can be proved mathematically. These zero crossings in second derivative of an intensity function will determine edge locations oriented in the orthogonal directions. The typical zero crossing filters are a Laplacian of Gaussian filter or a direction derivative of the Gaussian filter. A major difficulty with natural images in that changes in pixel values occur over a wide range of scales. No single filter can be optimally suitable for all cases. So, a way has to be found out to deal separately with changes occurring at different levels. This can be achieved by first taking local averages of the images at various resolutions and then detecting the changes in intensity that occur. To realize this idea, we need to determine the nature of the optimal smoothing filter and the technique to detect the intensity change at a given scale. There are 2 physical considerations that combine to determine the appropriate smoothing filter. The first is that the motivation of the filtering and the image is to reduce the range of the scale over which intensity changes take place. The filter spectrum should therefore be smooth and roughly band limited in frequency domain. This condition can be expressed by requiring that is its variance therefore should be small. The second consideration is the next, expressed as the constraint in the spatial domain. The constraint is that the contribution of each point in the filtered image should arise from a smooth average of the nearby points rather than any kind of average of the widely scattered points. With this, I now finish the various techniques which can be applied to a digital data to classify objects in an image. My next topic would be photogrammetry. Thank you.